Right, moving on to example 3 on page 28. Now this is a really important one because this kind of thing comes up all the time, so you've got to come up with a method. You've got to understand the method that we're using here so that you can apply it to lots of different problems. So what it's told us is we've got this reaction here. We've got carbon dioxide plus hydrogen reacting together to make carbon monoxide plus water. So just as a general rule, we're going to start off with a certain amount of each of these gases. So what do we know and what can we find out? Okay, so we know that at the beginning we've got 0.5 moles of carbon dioxide and 0.8 moles of hydrogen. That's what we know. We also know that at equilibrium we've got 0.04 moles of carbon monoxide. Right, so that's what we know. We also know that carbon monoxide has to come from somewhere, and it must have come from here. So if we're gaining 0.4 moles on the right hand side of the equation, it must have been lost from the left hand side of the equation. And we also know that if we're gaining 0.04 moles of carbon monoxide, we must have also gained 0.04 moles of water. We know that each time this reaction happens, we get an equal number of moles of these two here. Okay, so we must have lost 0.04 moles, sorry, that's not very clear, from this side of each of these reactants. And then we're gaining 0.04 moles on the other side. So what that means, if we started off with 0.5 moles of carbon monoxide, we must have 0.46 moles at equilibrium. And if we started off with 0.8 moles of hydrogen, we must end up with 0.76 because we've lost this 0.04 here. Okay, this is a method, a general method that you can use for lots of problems like this, so do go back over the book, read it carefully and check that you understand this before you move on. Okay, so we know that we started off, if we go back to what we know at the beginning, we know that we started off with 0.5 moles of this and 0.8 moles of this, and we've been told that it's in a 10 decimeter cubed flask. But we also know that to calculate Kc, we need a concentration, not the number of moles. So this bit's quite important. So to go from the number of moles, we need to divide by the volume. Now concentration is moles divided by the volume, or amount in moles divided by the volume, and we've been told that our volume is 10 decimeters cubed. It's in the right units already, so all we're doing here is dividing each of these values by 10. So to calculate Kc, we're doing 0.004 times 0.004 divided by 0.046 times 0.076. So if we calculate that, we end up with 4.6 times 10 to the minus 3. Now, those of you that are quite confident with maths will realise that actually we didn't have to divide by 10 first before we did this in this case, because all of these divisions by 10 actually cancel out, but it's worth doing it and it's worth going through the process because you would usually have to do that if there were an uneven number of products and reactants, or different numbers of products and reactants. As for the units, we don't have any units here because what we've got is moles per decimeter cubed on the top and the bottom of the equation, and so they cancel out.